Hi there, warriors. It's Miss Lemons, and we're going to continue our thermochemical equations conversation by moving into something called enthalpy diagrams. So just as a reminder, last video, I was just introducing you to the idea of enthalpy. Remember, enthalpy is equal, or the change in enthalpy is equal to Q. So we can change the change of heat content in a system, which is what we did in calorimetry. Okay, so now let's talk about how we can graphically represent the change of heat energy of a chemical reaction. So here's just examples of what you can expect as far as what these graphs look like in the chemical reaction. Okay, so let's pick each one apart. We're going to talk exothermic and endothermic reactions and how those graphs will differ. I'm going to use the same example that I used from the previous video, which is the decomposition or the formation of water. So here we have the formation of water. It's a combination reaction between hydrogen gas, oxygen gas, which gets us water. And remember, that's an exothermic reaction, and we can tell by looking at the thermochemical equation, which shows us that there is a release, or that heat is produced as a result of this reaction, therefore it is released. We can also show that by writing the heat content separately of the chemical equation in a negative, using a negative number and the units kilojoules per mole. Okay, so we can see that the heat content is ever so slightly changing here. I guess I could just set myself right there. We are starting with reactants that have a high energy, and then we've measured that energy, the enthalpy here in kilojoules per mole. So we're roughly at 650-ish or 670-ish kilojoules per mole for this reaction, and that's just the potential energy. Once the reaction takes place, the products measure at a different enthalpy, a lower enthalpy. So you can see here that we're now at like 100 kilojoules per mole for our products. So what we're trying to find here is the change of enthalpy. So here you would simply take the final enthalpy, so of the products, about 100, and the initial enthalpy, which is about 670, and subtract the two. So products minus reactants, or in this case, delta H, is equal to H final minus H initial, which would then give you negative 571.5-ish kilojoules per mole. Exothermic reactions release energy. Okay, it's going down the hill. I always like to think of enthalpy diagrams in terms of like sledding hills. Exothermic reactions release energy. These are easy. If you're releasing energy, it's like relieving stress. It's releasing, right? From the hill standpoint, if you're going down the hill, that's a lot of fun. It's releasing energy in the form of playing sledding. Thinking of this type of mnemonic is not working, but that's okay. We're going to move on. Endothermic reactions. Endothermic reactions, remember, this is heat entering the system, and we can write that two ways in a thermochemical equation. We can either incorporate it as a reactant, meaning it's one of those ingredients that we need, and we're going to show it by writing it directly into the recipe, or we can have it as a footnote. We can have the chemical equation and then show the delta H value, a change in enthalpy value, off to the side with the proper symbol. And remember, because this is an endothermic reaction, heat is entering the system, it's absorbing energy, and therefore delta H needs to be positive. So you can see here that our reactants are at a much lower enthalpy than our products in this case. Notice too that the products and the reactants from the previous slide, so you can see here, our reactants were H2 and O2, and then here our products are H2 and O2, and that's because it's the same reaction going in reverse. And they're still pretty high energy products, but we are starting with a low energy reactant. And so in order for us to get to that point, I always like to think of this Again, with the sledding hill, we can figure out just by looking at the curve of this graph if this is endothermic or exothermic without even calculating anything, because if you read the graph left to right, you have to climb up this hill, and that requires energy to climb up a hill. It's way easier to sled down a hill, right? That's a release of energy, therefore exothermic. For the endothermic graphs, you have to climb up this hill, and that is requiring energy enters your system in order to use and fuel your legs up those hills. Okay, the products have more energy than the reactants, and you can still calculate the delta H, the difference. Notice that it's just where the products are and the reactants, not the top of this hill. That's the activation energy, which is something we don't really get into for this class. But the difference between products and reactants, remember you have to do H final minus H initial, and that will give you a positive number, because we are creating an endothermic reaction, which means heat is entering the system. Therefore, positive delta H, positive Q, positive delta T. So in summary, the difference between exothermic and endothermic, so this kind of dips into the previous video a little bit, but remember, endothermic reactions, energy has been absorbed. Heat is a reactant. It's one of those ingredients that we add into the recipe we need in order to create our products. Endothermic reactions have a positive Q value, heat, a positive delta H value or change in enthalpy, and a positive delta T value or change in temperature. We can write an endothermic thermochemical equation one of these two ways. You can either put it directly into the equation as in kilojoules as a reactant, or you can write it off as a footnote, just like this right here, but don't forget your sign, and your units are kilojoules per mole, a little bit different. This is my preferred method because I like to keep my signs straight. Endothermic reactions in their diagrams have start with a lower energy reactant and end with a higher energy product, which makes sense because we are adding energy into the system. The energy is entering the system, therefore this is an endothermic graph. Exothermic reactions are the opposite. In this case, energy is released. It exits the system. That's a negative Q value, or heat, a negative delta H, or change in enthalpy, and a negative delta T, or change in temperature. And heat is considered a product because it is exiting the system. And to show that, we can do one of two ways. We can either have it at the end of a reaction or chemical equation and incorporate it as like one of those resulting products, what you've produced as a result of the combination of these two atoms or these two substances. Or we can write it as a footnote, which is my preferred method because not only does it give us the sign here, it's a built-in conversion factor, which is what I'm going to get into on the next slide. And remember, for an exothermic reaction, your reactants are a higher value than your products. We are releasing heat energy, and that's the difference. So the change in enthalpy can be measured by the change, the difference in the energy of the reactants and the energy of the products.